So in this video, we're going to look at some new functions. They're called hyperbolic trig functions, and they sort of behave like trig functions in some of their properties and some of their identities, which is why we talk about it as like hyperbolic trig. But it really has nothing to do with trig. It has nothing to do with sines and cosines. It actually has its roots in exponential functions. But it's really sort of a neat way that we can merge this exponential function with trig functions, and it also shows how we can merge complex plane with the real plane. So it's pretty cool. And so we do have our favorite series up here, right? So you know, are at least three of them: e to the x, cosine x, and sine of x. And so the reason I have them up here is that I want to prove something that maybe you saw last year in honors pre-calc, or maybe you didn't, or maybe remember. I don't know. But there's well, I think a lot of you probably remember the first part of this, which is that if you have a complex number, every complex number, so if you're in the complex plane, so you've got, like, you know, a plus bi, some complex number, you can actually draw that and think about, okay, well, what is the angle that gets you to that? And what is this radius? And this x direction and this y direction, the real direction and the imaginary direction, you could say, well, that complex number could be written as whatever, like r cosine theta plus I, or I guess r I sine theta. And sometimes, there we go, and sometimes that r would even be factored out. So you know that you have a real component and an imaginary component. Maybe r cis theta. Boy, I'm just having a hard time writing this. R cis theta is something that sounds familiar too. Like every complex number can be written as this polar form. Now, another thing that maybe you remember, maybe you don't, is that that polar form could be rewritten as e to the I theta equals cosine theta plus I sine of theta. And so that's what I want to prove right now, just to help develop these functions. Now, so what am I going to do with this e to the I theta? Well, you know, let's go ahead and think about our Taylor series for e to the x, right? Which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus x the, right? It just keeps on going like that. So now let's substitute I theta. So e to the I theta is equal to 1 plus I theta over 1 factorial plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the fourth power over 4 factorial plus I theta to the fifth power over 5 factorial, right? So it keeps on going. Well, powers of I kind of cycle through, right? So we know that, like, I is just the square root of negative 1, so we leave it as an I, but we know that I squared is negative 1, and I cubed could be reduced to a negative I, and then I to the fourth power is equal to 1. So every time in our expansion, every time we look at this I here, I'm going to actually simplify it to one of these four things, either I, negative 1, negative I, or 1. So now my expansion here, put this purple color, so that equals 1, and this is just going to be plus I, right? And there'll be like theta over 1 factorial. I squared is negative 1, so minus 1 minus theta squared over 2 factorial. Now I cubed will be equal to a negative I, so say minus I, and then I have theta cubed over 3 factorial, and then I to the fourth power, which is 1. So I just have theta to the fourth power over 4 factorial. And then I to the fifth power cycles back up to just an I. So we have I theta to the fifth power over 5. And then this would become minus 1 theta to the sixth power over 6 factorial. This would be minus I theta to the 7th power over 7 factorial. And finally, we're back to 1 as a positive theta to the 8th power over 8 factorial. And it keeps going. But what if we start grouping these in terms of the reals versus the imaginaries, right? So what are the real components? 1 minus theta squared over 2 factorial plus theta to the 4th power over 4 factorial minus theta to the 6th power over 6 factorial plus theta to the 8th power over 8 factorial, right? What do we see here? Well, that's why we have our other two friends up there, right? Those are the terms, right? 1 minus theta squared over 2 factorial plus theta to the 4th power over 4 factorial minus theta to the 6th power over 6 factorial, right? Those are the terms for the Taylor series, the Maclaurin series for cosine. So that would be cosine of theta. Now the other terms, notice, all have an I. So you could factor out an I out of them. And you have theta over 1 factorial minus theta cubed over 3 factorial, right? You see it's the odd powers. Theta over 1 factorial minus theta cubed over 3 factorial plus theta to the 5th power over 5 factorial, right? Minus theta to the 7th power over 7 factorial. In other words, we get I times the sine function's expansion. So plus I sine of theta. So any like polar form cosine theta I sine theta or r cis theta could be equal to e to the I theta. And now maybe you've heard of Euler's constant before, and that's something that this is really based on. So like we're going to look at that later on. But here's that proof, right? Here's that connection. So now we're going to take this to help us derive these hyperbolic trig functions. And we're also going to look at e to the negative I theta, which simply is just cosine of theta, and then becomes minus I sine of theta. Okay, so we look at those two. So if I add those two numbers, so if I take e to the I theta plus e to the negative I theta, and then what's happening on the right side? Well, I get cosine theta plus cosine theta. I get 2 cosine of theta. And then the signs cancel. So then if I divide out that 2, I sort of get this cosine of theta expression, right? That cosine of theta is equal to e to the I theta plus e to the negative I theta over 2. And if I were to subtract the two functions, so if I say, okay, e to the I theta minus e to the negative I theta, so then I would know that the cosines would cancel, and then I get 2 of the I sine thetas. And, again, if I divide out the 2 over to this side, so I get e to the I theta minus e to the negative I theta over 2 is equal to this other component, I sine of theta. So what I'm going to do is I'm going to let x equal I theta. So up here where this I theta is, I'm going to call that x, and then my theta becomes x over I. So I get e to the x plus e to the negative x over 2 equals cosine of this x over I term. And then I get e to the x minus e to the negative x over 2 is equal to I sine of this x over I term. And so we're going to take those kind of like, they're not really trig functions because we have this imaginary component within them. But we're going to define what's on the left of each of them as their hyperbolic functions. So this much right here we're going to define as the hyperbolic cosine. And this much right here, we're going to define as the hyperbolic sine function. And if you're wondering, well, why do they get the term hyperbolic? It's because they actually fit the definition of not a unit circle, but a unit hyperbola. Here are two branches, right? Here are two branches of a hyperbola. And like if it's just like almost like a unit circle. So instead of saying like x squared plus y squared equals 1 for a circle, this would be x squared minus y squared equals 1. So both of those functions, the one that I have for x and y, satisfy that equation, and then that's an equation of hyperbola. So that's really why we put like this word hyperbolic cosine, hyperbolic sine, because there is some similarity between their trig properties and the graphs, but it's really rooted in exponential functions. Now, I want you to like kind of know where these come from and understand kind of like what it's based in. But ultimately, you don't have to have that proof memorized. If you turn the page, you take a look at the definition. Here are the 6 hyperbolic trig functions, and there are 6 because there were 6 trig functions, right? So and notice the extra h that comes after each of them. So it's hyperbolic sine, and we just derived that hyperbolic cosine, and then. If you want to know what is hyperbolic tangent, you would just take its sine divided by its cosine. So then the 2's would cancel. So if you really wanted to write that out, then you would get e to the x minus e to the negative x over e to the x plus e to the negative x. And then you have hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. Now, like sometimes when you're doing these, it gets a little bit long to say hyperbolic sine, hyperbolic cosine. So sometimes we call that sinh and cosh, for shorthand, and that's fine too. But I don't know if there's a universal shorthand or whatever, a verbal shortcut, right, for the other 4 hyperbolic functions. So if hyperbolic sine, hyperbolic cosine, or sinh and cosh. The others, I would just say, it's hyperbolic tangent, hyperbolic cotangent. So that's the basis of the the definition of the hyperbolic functions. So then the next video we'll just practice a few things with properties and kind of look at what happens as you start analyzing both their functions and then also their inverses. Our ultimate goal then is to do some calculus with it as well.